Hello everybody. Today we will discuss about simple harmonic motion, which is the most significant one which we will deal in physics in every aspects like propagation of a sound wave in a medium like etc and etc, everything are there. So thus we would like to discuss about simple harmonic motion in today's video. So before going to that, I would like to explain you some small definitions like different kinds of motions. So in that, the most prominent one is periodic motion. So first initially we will learn about periodic motion in detail, and then another definition like oscillatory or a vibratory motion, and then we will go into the definition of simple harmonic motion. So firstly, what is a periodic motion? So the name itself suggests that periodic means like a fixed interval. So periodic means like we can say like fixed interval, like in our school also it will be like college. So a period means it will be like 1 hour or a 45-hour duration, which is a fixed one, and that to interval which repeats itself, right? I mean every class has a period for 45 minutes, or every class will have a period of 1 hour, etc. So we are saying like period means it is having some fixed interval of time. So in such a way, periodic motion is defined that a particle, or you can say like if a particle, we can write simply as a if a particle which repeats itself, after equal intervals of time, after equal intervals of time, and such a motion we call it as periodic motion, like a motion in which a particle executes or repeats itself after equal intervals of time, and then we say that particle is said to be in periodic motion. So what is this like interval of time we call? So this interval or equal interval of time, whatever we are saying, we call this one as time period. We call this one as time period of particle executing periodic motion, of a particle executing a periodic motion. So for periodic motion, we will see a basic general example in daily life which everyone knows in detail, that is motion of planets around sun. So motion of planets around sun. So why need to take all other different planets? We will take our earth only. So earth takes around 365 days around the sun to complete one revolution, and this will be repeatedly equal every year. So this 365 days we call as time period of earth. 365 days we call it as time period of earth, and the motion executed by the earth around the sun we call it as a periodic motion. So this is how we say periodic motion. And don't say that so for every 4 years the earth takes 366 days, no sir. So that is quite a leap year, we'll say. But to explain a periodic motion, a general example I have taken, that earth takes 365 days to move around the sun, where 365 days we call it as its time period, and the motion executed by the earth in such a manner around sun we call it as a periodic motion. So like these are the examples we can say. If you want more general, one more thing in general, we can say Halley comet. So Halley comet, which passes by earth for every 76 years. So you can ask your parents like who were born around 1960s, like 1965, they might have experienced this Halley comet in the year 1972 to between, like I don't remember exactly, like 70s to 90s in middle. This Halley comet passed through earth or passed by earth. So after 76 years only again this Halley comet is visible. So it is following a path like which takes around 76 years to move or to complete its one revolution around our solar system straight away. So this is how we will be detailedly explaining the periodic motion. And now let us go to the next thing, that is oscillatory motion. That is oscillatory motion. So many people will be having a bit confusion about oscillatory motion and another sort of motion, we call it as vibratory motion. So what is the main difference between these two? Based on my knowledge, I say that both can be explained as same, but a small difference in a words which define the motion, that is oscillatory from vibratory. That's it. So initially we will learn about oscillatory motion. So if a particle moves, so I would like to use a word here like to and fro. If a particle moves to and fro about a fixed point repeatedly, about a fixed point, instead saying fixed point, I can say this one as some position, fixed position, repeatedly, and such a particle is said to be executing, or such a particle is said to be possessing oscillatory motion. Such a particle is said to be possessing oscillatory motion. And what do we call this fixed point or fixed position? Is mean position. We call this as your mean position. So for to understand this oscillatory motion clearly, I would like to take the example of motion of a simple pendulum. So in olden days, like in your grandmother or grandfather, you can say some wall clocks, big wall clocks will be there, or you can see in Tom and Jerry also you'll be seeing a big wall clock where the Tom gets hit and that bob will be moving to and fro. So that one we call it as a simple pendulum. So I would like to show you clearly over here. So to a roof, I have just attached a simple pendulum, so having some length L. So those all I would like to, no need to mind know all those things. And this is your bob, and this position where it rests at center or in equilibrium, we call it as your mean position. And the other name for this mean position is also called as point of equilibrium. So directly we can say. So now if I just move it up, so I just pulled it to some height, so like this, and then I just left this bob from here. I just left the bob from here. So when I just leave the bob from here, what happens? It starts moving down in this way, and then it reaches this mean position. It crosses the mean position, and then again it moves up, and then it reaches another position, and from there it comes back to the mean position again. So I would like to say moving towards that particular point and moving this way, so to and fro. I would like to define this one as to and fro. And these points which are moved to the edges, I would like to call this one as extreme position. And this is one extreme position, and here is one more extreme position. So thus the particle always passes through the mean position and reaching the extreme position and again comes back to the mean position. Thus it repeats itself till the bob rests at its point of equilibrium, that is nothing but your mean position. And this is called as your oscillatory motion in detail. And now let us see about vibratory motion. So if a particle is said to be executing, or if a particle is said to be moving, if a particle is said to be moving back and forth, if a particle is said to be moving back and forth, the difference is this one only. So in what you call this like oscillatory motion, we use the word to and fro. Here we are using back and forth. So if a particle is said to be moving back and forth, again as usual about a mean position, that is your fixed position, about a mean position, then the particle is said to be executing vibratory motion. The particle is said to be executing vibratory motion. So for this we are having many examples. So like example, if you are learning guitar or violin or sitar, so motion of a string in violin or a guitar, motion of a string in violin or guitar is the best example for your vibratory motion. So if you want to detailedly understand what is this back and forth, so I would like to consider one more example also, propagation of sound in a medium. Propagation of sound in medium. So I would like to explain this also in detail. Propagation of sound in medium. So let me consider like the medium contains the particles, and I am assuming the particles as these straight lines, I am assuming as the particles present in the medium, and saying that the particles all are equally spaced. Clear? So all the particles are equally spaced and present in the medium diastratively. So let me consider in this way now. So I have just given some sound energy like this. I am speaking now, right? So I'm speaking means some energy is being sent to the particles present in and around my like vocal cords or near my mouth or in front of me somewhere. So who are able to hear, that is energy being transferred from these particles, right? So all these particles get disturbed by the sound energy produced from my mouth, which causes a wave, that is nothing but a disturbance, and this energy is being carried to the particles, the next particles, and then reaches the person who wants to hear my voice straight away. So here I'm just giving some sound energy to these particles. So assume that due to this sound energy coming over here about a mean position, see, I would like to consider, or else somewhat closer I would like to take here. So say this is your mean position. So assuming this is your mean position, MP not Madhya Pradesh or middle point, this is your mean position. So now due to the sound energy given to the particles, all these particles present in the medium move closer, and thus it creates a compression. Thus it creates a compression in the particles present in the medium due to the sound energy, and the remaining particles will be equally spaced as usual. Only few particles got compressed, and now as the energy is given to these particles caused a compression which make all the particles come closer about a mean position, and now this sound energy is being transferred to the next particles. As a result, these particles tend to relax or tend to get one more energy or energy pulse from the source, so therefore they tend to relax. Now during the relaxation the particles will be relaxed more, and it creates a phase called rarefaction. We call this phase as your rarefaction, and this is all happening about again the mean position, and these particles will be equally spaced. I mean like the next particles are whatever the later on the particles present there are compressed again in this way. So thus the sound pulse, whatever I have given the energy, is being carried from one particle to the another particle in the form of compressions and rarefactions in the medium. So thus the sound energy is being transferred from source to the destination. In meanwhile, so here you can say the particles were moving forward. So fourth I can say this is about the mean position, and the particles are moving backwards. As a rarefaction I can say this is as back. So back and forth of particles or movement of a particles about a mean position, I can call this as your vibratory motion. So thus we have explained clearly about periodic and oscillatory in detail. So now let us see the definition of simple harmonic motion, so which is the main theme of our chapter or this video we can say. So simple harmonic motion. So if a particle is said to be executing, if a particle is said to be executing simple harmonic motion, so I would like to write in short simple harmonic motion as SHM. So executing SHM if it moves, see the word we are using here, to and fro. If it moves to and fro about its mean position, such that there is a condition here now other than periodic motion, such that its acceleration, whose acceleration, particle ka acceleration, its acceleration is directly proportional to, its acceleration is directly proportional to its displacement. Its acceleration is directly proportional to its displacement. Whose displacement? Particle ka displacement. In magnitude. See, I am using a word here, displacement in magnitude only. So equal or proportional to its magnitude or its displacement in magnitude, but the direction of acceleration is opposite direction to that of displacement. So we can say directly the acceleration of a particle is directly proportional to its displacement in magnitude but in opposite direction, and this acceleration is always directed. This acceleration is always directed. So it should be directed into one particular direction. That is nothing but always directed towards position of equilibrium. Already we know that it is its mean position. So thus this entire thing we call it as your simple harmonic motion. So if I would like to describe like A as your acceleration of particle, A as your acceleration of particle, and Y if you would like to take its displacement, on a whole the definition can be written as an expression form as acceleration proportional to displacement in its magnitude but taken in opposite direction. So here minus indicates the direction is opposite to that of displacement, and removing this proportionality I would like to write this one as A is equals to some minus ky. What is this k, you can ask me. So this k is called as your proportionality constant. This k is called as your proportionality constant, and this proportionality constant and etc. we will learn in the next video, where we will describe the projection of a point moving in a uniform circular motion about its diameter executes a simple harmonic motion. We will see in the next video that. So here k is your proportionality constant, and now let us see some conditions to execute or for a particle to execute in a simple harmonic motion. So for a particle to be in SHM, it has to follow some conditions. What are they? The first condition is the motion of the particle. See, most important this is. Motion of particle should be always a periodic motion. So that's why at the starting of video, I have explained to you what is periodic and what is oscillatory or vibratory motion. Second one, acceleration and displacements, whatever it is, should be both in opposite direction only. So if acceleration and displacement are said to be in opposite direction, if both are in opposite direction, then only this is the required condition for the particle to be in SHM. And third one, the acceleration should always be directed towards mean position. It always be directed towards a mean position, and this is the another condition for a particle to be remain in simple harmonic motion. So thus we have defined SHM for a particle clearly, and for a particle to remain in SHM what are the conditions also. So thus we have learned in this video detailedly about periodic, oscillatory or vibratory and simple harmonic motion. So hope you all understood, and any doubts are there, please post in a comment section so that I can clear your doubts. So thank you very much. Have a great day.